It's exactly 8 p.m. Sir, shall we start?
Yeah, sure.
Okay. Uh, Once again, a very good evening, everyone. I am Dr. Kailan Ming Sangi, your host for tonight. On behalf of the organizers, Government Stewardship College, I once again extend a very warm welcome to all of you. Tonight is the sixth night of our one-week international webinar on science in the 21st century. In the past 5 days, in the past 5 nights, we have had an insightful and informative talk from different distinguished speakers from various fields of sciences, and we hope that you have a fruitful session as much as we do. First of all, tonight, I would like to thank our esteemed resource person for accepting our humble request and besides that, rescheduling his time according to our convenience. And thank you so much, sir, for that. And to all our participants, we are really thankful for sparing your valuable time. And please do stay with us till the end of the program. Uh, this program is streamed live in Government Stewardship College official YouTube channel. If you would like to share it, we have put the link in the chat box, and you can share it if you would like to share it. And if there are any questions based on the talk of a resource person, you may put your queries or doubts in the chat box so that our resource person will clarify at the end of his presentation, or you may unmute yourself at the end of the presentation to ask him any questions if you have any. And then for the YouTube viewers, if you have any questions, you can put your questions in the comment section. And then, so moving on to our program, tonight it's my pleasure to introduce our resource person, Dr. Aditya Kumar Jain, who is the postdoctoral research assistant, physics department at Royal Holloway University of London, United Kingdom, since January 2020. He has completed his PhD, Doctor of Philosophy, in the year 2019 and was awarded in the year 2020 from Indian Institute of Technology, Bombay, India, with a thesis entitled Cross-Correlation Measurement of Low Frequency Conductivity Noise and Effect of Invasive Voltage Probes on Weak Localization Measurement. And he has 5 years of teaching experience as a teaching assistant in the following laboratories: in the electronics lab, in the solid state physics, and in the general physics at Indian Institute of Technology, IIT Bombay, India. And he has published various scientific papers which are published in various renowned journals, and he has been awarded several prestigious awards from various organizations. To mention few, he was awarded the Best Poster Presentation Award in prestigious 62nd Department of Atomic Energy Solid State Physics Symposium in the year 2017. And he was also awarded the Best Poster Award in 5th Annual Symposium of Physics Department in the year 2015. And he was also awarded in the awarded for third position in Tech Connect 2014 with the team physics in IIT Bombay during the prestigious Tech Fest 2014 IIT Bombay. So may I now call upon our esteemed resource person, Dr. Aditya Kumar Jain, to deliver his talk. Sir, please.
Thank you for very generous introduction. I have actually everything is right for my CV, but these are not sort of very large achievements so far, except PhD. So you can just call me Dr. Aditya Jain, and there is nothing else. Now I will share the screen. During my PhD, I have done some work related to the measuring noise basically in some conducting films. So the thing is that what caused them and why this noise is there, and I will just discuss in a short presentation, and I will try to give us some brief idea that how the condensed matter system, especially the conductors, they give rise to some fluctuations in voltage across it at some finite temperature. So to a public like which includes a various stream of science. This will require a little bit physics, a little bit deep physics, some mathematics, some engineering, electrical engineering, but overall, I will try to give you something which hopefully you might get something and you try to implement for your like future experiments. And based on the same work, I have designed one experiment in IIT Bombay for the UG student, and they are currently doing the same experiment on thermal noise. Excuse me. Yeah. So this is the basic outline of my seminar. Uh, why electronic noise is important and how to measure electronic noise. First of all, a mathematical approach, and then we will go to a practical approach, then how we can measure it practically. Then what I will show you is a thermal noise, because there are a lot of, uh, I will say, more than 10 or 20 type of noises present in the condensed matter system. But we will try to focus on one type, which is the thermal noise, which can be generalized, and it will give you as a universal law for it. And this universal law, you can calculate the universal constant like Boltzmann constant, and you can get the absolute temperature. So this could this could be a route to get the temperature. And then how I have designed or how one can design a setup for measuring this type of noises in conductors or semiconductors or any condensed matter system. And then I will discuss some preliminary results which will satisfy you, because I will use only basic registers that everybody is familiar. Like you might have seen these registers in transistors. When you break your radio, you will see some small parts in it. And this is just a part of your any general electronic equipment. And then life is not very simple. So there is always some limitations on each method. And I will discuss then how we can figure out the limitations and what are the limitations of the method. So why in my work, like in my PhD work, why I was motivated to do this? Because first, uh, on any condensed matter system, it could be a conductor, it could be a semiconductor. Conductor means normal metal, semiconductor means silicon, germanium, or gallium nitride, gallium arsenide, even different type of zinc oxide, doped zinc oxide. So these are the semiconductors. So what happens when you try to, even if there is no current in the system, means you are not putting any bias to it, means you are not supplying any voltage to it. Even in that case, if the system or the film or the material is sitting at some temperature, suppose at room temperature, and you try to put two probes of your voltmeter across it, and if your voltmeter is like it has a least count of few nanovolts to few microvolts, means it can measure very tiny amount of voltage, then what you will see, you will not see a zero voltage, you will see some varying voltage like few nanovolts, few microvolts, and this voltage keep varying very fast. And depending on your probes, like voltmeter, how fast it can measure, you will see these fluctuations are like anything. They are doing like up, down, up, down, up, down, plus, minus, whatever. But the voltage amount of the voltage will be very tiny, like few nanovolts to few microvolts in positive or negative. The speciality of these fluctuations is if you can record for a certain length of time, like suppose you record it for 1 minute, in 1 minute, if you are recording 100,000 data per second, means 100 kilohertz is the frequency of recording with this sort of data, then you have MB of data, maybe GB of data. The data will be very high, and you take just add, keep adding all these voltages, and the long time what you will get zero. It won't be sufficient, give you a very, it will be maybe pico or femtovolt. Even some of these voltage are micro, some of these are nano, but overall average will be less than 10 to the power minus 12 or so, or even zero. In most of the cases, if you do it for 10 seconds, it turns out to be zero always. This is my experience. So now somebody try to ask a question when you can't draw any conclusion by measuring what you did. Okay, you put a two probe and you are averaging out and it is giving you zero. So what you're trying to say means you have not even biased the system, and you are saying it that you can draw some conclusions from these fluctuations. So I will try to introduce that some sort of theory can relate it to the temperature, and how we will do it. We will not do the averaging, but we will do the squares and then average it. Okay. So every negative voltage also turn out to be positive. So we will have a all quantities in positive and then we average it simply. That will relate to some power, some finite number, and that number can give us the information of the temperature of the object that the probe we are putting onto any system. So that we can extract the temperature by just reading this tiny amount of voltage. If you increase this temperature, increase the temperature of the system, the long time average of the squares of this voltage will increase. If you decrease the temperature, the sum of the squares will decrease. So this is how we can extract the temperature. Now, how to do it practically and how we will, let's learn in the next slide. So there are some other applications. This is the first application that I wanted to show you, the electron temperature measurement. And then if you bias this system, and then what will happen? Electron will pass through the system and it will scatter through the various mechanism. Like inside any condensed matter system, the system is made of atoms, molecules, ions. When electron pass through the system, what will happen? It is scattered through this atoms, ion, and sometimes it may trap into some defect, and sometimes it come out. So all this, what happening to the electrons inside this material will also reflect in this sort of fluctuations. So even if you bias the system, these fluctuations are important, and you can get the information that what sort of mechanism is involved in the conduction processes of the charge inside this system. Now come to the next, this, if you measure these fluctuations, and these fluctuations are, most of the fluctuations are of not very fast but slow, suppose few hertz to few kilohertz, then what you can say about the system, okay, this device is, when you are making this device, this got dirty. Generally there are a lot of methods of making semiconductor devices of films. So the best way of doing it is arrange the atoms in very regular fashion, like you are arranging one by, like you arrange your stuff in your almirah, like one by one, stacking each other your clothes. Similarly, you need, in a process, which is the one of the best process, called the molecular beam epitaxy. The epitaxy means arrangement, and what you do in this arrangement, you will take atom and arrange one by one and make one full layer, then stick another layer on top of it in a very regular fashion. And if you have this sort of control at atomic level, this will give you the best device, almost defectless device, and you will not see the low frequency fluctuation. But if you are not using one of the best technique, because this is very expensive and no, basically most of the Indian universities, they can't afford it. So they are doing CBD techniques. This is called um, CBD means, you know, CBD, it is basically chemical vapor deposition or the physical vapor deposition, in which you heat a sub sample and you deposit on some substrate. Okay, you heat the sample to its melting point, and once it reaches to the melting point and you start heating it at one point, it start from liquid phase to the gaseous phase, and this gaseous phase is called the evaporation process. And this evaporated atoms or molecules you try to deposit on a surface. So this is called one film. But this sort of process will happen at higher pressure, and you have very poor control of staking, staking arrangement. Like you cannot very efficiently do the epitaxial growth in this sort of system where you are using CBD or PVD system, which is called chemical vapor deposition and the physical vapor deposition. Chemical vapor deposition means if you are using chemical route. Physical vapor deposition means if you are using physical route. Chemical route, it involves the chemical reaction and some byproducts. So, and what the physical vapor deposition is, only suppose you are having gold and you melt the gold and you start heating it and it turns into the gold atoms, evaporated atoms, and you have a glass slide and you just coat it on a glass slide. This is called physical vapor deposition because you just heat the gold and it deposited on the glass slide. But on a chemical vapor deposition, suppose you have some two gases, suppose one methane and one arsine, and you try to do some process in the chamber at some finite temperature, or suppose it turns into some other compound which deposit on the substrate, and the other byproduct they just go away into the pump out from the uh, pump out from this vacuum pump or so. So this is called the chemical vapor deposition. So if you want to study the quality of these devices, what you made, the films, you can do the low frequency conductivity noise measurement. If this noise is very high, means these devices are worse, they're not good. If this noise is very low, means you made very regular film. So if you basically measure a device which came from the MBE chamber, will be best performing rather than which came from the CBD or the PVD system. And another thing, you can also correlate this process, which is quite complicated at this level, I will say, and I should not go through this because this is very complicated for you if you are not from, masters of the physics. So I will not go through the last two one, and let's focus on some simpler thing. So I think I should we start with something familiar. I think we must have been seeing this oscilloscope. Life science, medical science people, they are very much, seeing this oscilloscope by heartbeat or any other pulse you want to see. So you must have been aware of this, pulses that you are measuring. This is oscilloscope. If you have a pressure sensor, that pressure sensor, what pressure transducer does, if you put a strip or something on your wrist, the pressure convert into the some tiny signal of the voltage, it amplifies and it feeds it to the oscilloscope, and you see some variation in the pulse. But suppose in our case, we have put the two probes of this oscilloscope across this sort of known resistor. I think most of the people are aware of this kind of component, which is called the metal film resistor, which is fairly available in old style TV, radios, etc. Nowadays, it has been replaced by the surface mount resistor, but the principle is same. Suppose this is a 1 kilo ohm resistor, its value is 1 kilo ohm, means if you apply a 1 volt across it, it will give you 1 milliampere of current. But we are not applying any bias to it. There is no voltage involved, there is no current involved. You just took a 2 probe of this uh, oscilloscope and you connected across the two terminals of this resistor. Initially, when you see the oscilloscope, you will see, oh, there is nothing. I have seen nothing on it because the voltage per division of this oscilloscope is only few millivolts. But suppose you have a device which can further zoom in, like you can see the microvolts or nanovolts, and you put your zoom and you see, oh, it look like this, which make no sense because it is varying with time. It has no regular fashion on which it is varying. It is just random. Exactly, this random signal will give us the information of the temperature of this resistor. Okay, let's find how. So the first question I asked myself in my PhD, what the hell? We measure in the noise. How can I measure a noise? Noise can be everywhere. Noise can be from, the radio station, which is operating, which it's everywhere. Even from my mobile, I can see this from my mobile because it is hard to believe me, even for myself. Then even I'm not biasing this, there is no current flowing across this resistor. How can I believe this is true or not? So this is like the self-belief. My supervisor said, don't panic. It will work because theories, the most theories, they have some relevance to the physics. Let us believe it and try to figure out whether it is possible or not. So don't panic when you see these equations. Okay, this is very simple thing. Any signal, like we are measuring across a register, right? It was varying like this, random. If you take an average of it, long time average, put this is a symbol, this bracket symbol is just an average symbol, means you suppose there are n data points, you took add them divided by n, so this is the average, and then there is a term which is fluctuating in time because average plus some fluctuations across it. When you take a register which has no bias, obviously the average is 0. So your signal V of t is nothing but the fluctuating voltage, delta V of t. Now, when you see this is oscilloscope, the data on oscilloscope, and take a data in a pen drive to process it, it will not be a waveform, but it will be a discrete data points, right? And discrete data points, and it may not give you the time axis. It will just give you some random entries with some number, right? When you transfer this data to a pen drive and try to process it. So let us say this time axis here is m, the number on which number your data is, and you just give the entry and try to add them from m equals to 0 to n minus 1, or you can say m is equals to 1 to n. Why I choose this? Because the software read from m equals to 0 while processing. So I just wrote this m is equals to 0 to n minus 1 over, however, these are total n data points, and then you average them all together, you are going to get 0 always. This has to be true for this fluctuating signal. Now, here this Vm is nothing but the fluctuating term. Now, there is a term which is called the autocorrelation. Autocorrelation is nothing but the self product with some delay, and later on this delay will go to 0. Basically, it is a self product, means you are squaring the signal, nothing else. So don't panic. However, in some complex signals where your signals are having real part and imaginary part and they are having phases and amplitude, in that case, what you need to do, you need to take a, suppose a complex number can be written as a plus iv or x plus iy, and you define its magnitude, r is equals to square root of x square plus y square, and its phase is tan inverse by over x. So this is how you define. Hello. Yeah. So then this now we are not dealing with that because all the voltages that we have recorded are discrete data points and they are real numbers. They have no phase information, nothing. They are just on the number space, by like 1 to 1 corresponding to this microvolt, 2 corresponding to nanovolt, 3 corresponding to some minus microvolt or so, right? Then come to a power spectrum. This is a simple uh, like when you have a discrete number, this is the, I think the computer application people, they might have known the spectrum of the discrete numbers is given as the Fourier transform, a discrete Fourier transform of the autocorrelation function. And finally, you will get some number which is in the frequency space, 1 over the frequency space. Don't bother about it. However, if you do this experiment in time domain, will also give the same results, but with slight errors. Let's go to the next slide where we can explain that what's going on. So there is always a complicated way to say some simple things. That's what the scientist does in PhDs. They complicate a issue which is very simple, but let us try to do opposite. Let's simplify a complicated issue. Okay, so this is the theory of the theory for the thermal noise measurement, which is known as the Nyquist relation, and this is basically done by the Johnson and Nyquist. So the noise is known as the Johnson noise, but this derivation is done by the Nyquist. So we say this is the Johnson Nyquist noise, and this relation is the Nyquist relation. And here, let's not go into the details of it because this ultimately comes from the Maxwell's Boltzmann distribution of the fluctuations, because electrons are the fermions. So it will be following the Fermi-Dirac statistics, right? So it explains that if these fluctuations are happening at frequency f across the resistor R, then the power spectrum can be given as 4RHF divided by this exponential term, which is exponential term is containing the temperature of electrons. Kb is the Boltzmann constant, H is the Planck's constant, R is the resistance value. Now, so this is just graph of this equation that I plotted in origin. The idea is taken from this IEEE transaction. This is simple. You can also plot this function as a function of the frequency, which is here as well as here. Once you simplify this, like e raised to power x is 1 plus x square upon factorial to n, etc. The square term will cancel out because it's very less. So 1 plus x, basically you will end it up 1 cancel out and you will end up getting the 4 kbtr. At very low frequencies, from something like 1 hertz or even few millihertz to gigahertz, most of our electronics works into the gigahertz. You must be aware of the microprocessor speed, how much gigahertz it is, right? So the most of the electronics works in this range, gigahertz. So in all this range, our devices that we are using, like mobiles, like computers, all these devices, they suffer from this noise, right? And this actually limits their performance as well. So this noise is this noise, thermal noise, cannot be avoided as it is fundamental in nature, and it has to be present if you are measuring across a resistance R, and if your device is sitting at finite temperature T, then this is a universal law that minimum noise present is 4 kBTR, right? But what happens if you go very high frequencies? Because any spectrum cannot be, cannot contain infinite power. Suppose it goes on forever and ever and ever. Then this area under curve, this spectrum will have infinite power, which is not true in any case. So no spectrum contains infinite power, because the electrons, they have, there will always be a finite time between the scattering of electrons. Either it scatter from the ions or another electron. It could be as low as 10 raised to power minus 12, like picoseconds, to as maximum as possible to maybe nanoseconds, or maybe 10 nanoseconds. But in 10 nanoseconds to 1 picosecond, all the scattering processes of electrons, they over. There is nothing beyond that. So if it is 1 picosecond, corresponding signal is how much? 1 over 10 raised to power minus 12. So basically 1 over 10 raised to power minus 12 will give you 10 raised to power 12. So your all the processes will end till terahertz region inside a like condensed matter material. I'm not talking about the optics, because when the light and matter interact to each other, those processes can be in femtoseconds region. Now, life is not very simple. When you try to measure noise, challenges everywhere, because the instrument from which you are trying to measure your noise, it's itself noisy. So what you need to do, you need to try to amplify your signal before you feed it to a device where you can measure it. Like if you're trying to measure your device, what you need to do, you need to amplify these fluctuations before you feed to a I will say digital analog to digital converter, where you will change this continuous values in your discrete values. So once you connect a preamp, there is a problem, because preamp itself will have its own noise. It will give you some gain. Suppose you are getting this, let's say this is the resistance R as a DUT. D means device under test. DUT means device under test is a simple resistor that I showed earlier. It's a simply the similar resistor. G stands for the ground, and with respect to the ground, ground means zero, you are measuring on some fluctuations which is across the resistor R, which is a small v of t. Since these fluctuations need amplification, we put a preamplifier. Preamp means preamplifier, which have some gain G. So what is going to be fed into the analog to digital converter, ADC? It is gain times the signal which need to be fed, which need to be amplified, plus some noise. This noise is a noise introduced by this preamplifier. We cannot avoid this. What we can take, we can choose from the market which can give you minimum noise. Now, same, we can choose the ADC which can give you the minimum noise. And what the ADC will do, it will convert your signal very fast to some discrete values, like the mathematics that I showed. The with some, you can get some number and some entries with respect to the each number. And what you need to do, the discrete Fourier transform. The Fourier transform is, I think this is, I will say, the inverse space problem. So let us not go into the deep into it, but hopefully few of the audience is aware of the Fourier transform. So, and then we take a DFT and its complex conjugate. We multiply an average for one trace, two trace, three trace. Suppose if you are patient, you can do it for infinite, and you make this, uh, you can maximize your signal. But whether it is true or not in this case, let's figure out. Suppose we put this signal and multiply and get the spectrum formula from the slide that I showed, which I will go for the, yeah. So we are going to get the signal here, SV of f, the spectrum is 1 over n, Vf and Vf star, which will give you Vf square. So same thing I will do here. Now I will replace this with, this time domain term will be amplified in the frequency domain. This will also amplify into the frequency domain. And what you will end up getting here is the square term corresponding to the spectrum that is desired, which is green that I have showed. Okay, this I want. But you will also get something from this term here, which is you don't want, because this is also giving you the self product. Self product means you are is x plus by x square plus by whole square. So means you want to measure x, but you are doing x plus y whole square. So you are end up getting x square plus y square plus 2x y. So the y square plus 2xy you don't want, right? Because you are only interested in the x. That is why how you practically extract the information of only x if y is also present. So this is the challenge. Now, a hope is always there. So what's the hope here? So then we come across an idea that we can, if the noise, the initial concept of the noise was noise are random and they are not related to each other. Suppose one noise is coming from here, which we are interested in, and that is fit to the now suppose two preamplifier. Now these two preamplifiers, they are battery operated, so they are not having any common connection. So now we feed with the two preamplifiers and two analog to digital converters, and then we do the same. However, we are taking the complex, now we will not do the autocorrelation, we will do the cross correlation of the two channels, which is we will take the Fourier transform of the first signal and the Fourier transform of the second signal and conjugate, then multiply to the first signal and then average it. So this is a clever way. Now what we will end up getting here, we will end up getting, suppose this is V1 of t, it amplified plus your fluctuating term plus the noise term introduced by the preamp, and here preamp 2 will give you the amplified term of the voltage plus noise from the other preamp. Now the nature of this N1t and N2t and Vt, if you take long time average of this, they are going to be 0. So let's keep that in mind. And then if you take the then if you see the same formula V1 of f and V2 of f, it will give you the term where you're interested in 1 over n V of f, V star of f plus n1 and n2 product. So N1 itself is long time average 0, N2 its long time average is 0. Thus, if two quantities they are random, the product is also random, and you will get the product also long time average 0. Similar to here N2 and V they are not like uh, correlated. So basically they independently going long time average 0. Similarly for N1. So this blue term will vanish when you do the averaging, and you will end up getting only the power spectrum. So the life is simple when you cancel out this excess noise, electronic noise, by using two channels of amplification using two independently powered preamplifier. This is the concept of the two channel cross correlation, which will only give you the fluctuation, the amount of the power present in the fluctuations across your device under test, which is the spectrum. So patience always pays. Effect of longer averaging time. If you took, suppose, if you keep averaging one data set, like you have taken one data, then two data, then three data, each data set having suppose 100,000 points, and you keep taking cross correlation and average it, then take another cross correlation and average it, then another take a cross correlation till this is I'm showing you 10,000 data points. So here is the 10,000 data points are being averaged for 60 minutes, uh, sorry, 60 seconds, sorry, 60 traces and 120 times, 60 times and 120 times. So time is 5 minutes and 10 minutes for each. And this is, I will say, this is the bandwidth is 25 kilohertz, because the device, which actually takes uh, the analog voltage and converts into the discrete voltage is called DAC, can only operate at this frequency for my application. So this is the limitation of the experiment, that we are only seeing the fluctuations which are up to 25 kilohertz. If you want to improve your experiment, you need to spend more money to improve your bandwidth. So this is the thing, but the system that I made is totally homemade, and we made it our like by my own hand. So it doesn't actually, the overall cost of the system that I made is less than 50,000 Indian rupees. So it was very cheap and cheerful, and it can give you the same physics for undergrad level, so they can understand about the thermodynamic fluctuations, and the you know about the temperature, that this is really a thermodynamic potential which determine the flow of the heat. So this is simplicity is the beauty. So here is the setup, which is cost less than 50k INR when I made this in 2015 or 16. So what it is made of? Simple R1, R2, R3, R4. These are the normal resistors that I have showed earlier. So this is the various resistors that will be fed into the two preamplifier. This preamplifier, you can see the image. So this PCB has two main chips, which is AD analog devices 743 component, which is just operational amplifiers. And you can see this is 9-volt batteries. This is to power this preamplifier. So what I did, I made this circuit which has two stage amplification 30 by 30. So you will get 900 gain. So basically whatever the fluctuations across R1 is being fed to the 900 gain amplification to the preamplifier 1, and same fluctuation are being fed to the preamplifier 2, and then This analog to digital converter is provided by the National Instruments. This is cost is around, could be 15K to 20K INR. So you can get it, and then you can write your script of doing, various stuff like taking discrete Fourier transform, and then take a spectrum. Then this script is written in the PC, and what you will see, something like that. So the cross correlation output is fed, and you will see the spectrum. You will see the spectrum for like 25 kilohertz of the bandwidth. And so the data points I'm only plotting till 10 kilohertz. And these are the spectrum for various resistors. You can see these are the minimum resistance that has been measured is 200 ohm, and the maximum is 100 kilo ohm. So there is 3 order of magnitude variation from 200 ohm to 100 kilo ohm. And these blue dotted lines are the theoretical values. These are the theoretical values of the spectrum that I should expect, like 4 kbtr. And they are very well following the trend. Now, one can ask, what is the weird thing happening at very high resistance? See, they are not flat. Actually, it should be flat. But as I already told you, there are always some imperfections in the devices which cause the 1 over f type of issues, like uh, which can cause, like 1 over f type means low frequency noises. So if these metal film resistors are not very well made, they will have 1 over f type of noise. Or even if your uh, resistors will not have noise, then the electronics can also affect and give rise to this kind of 1 over f type of behavior when you measure the high resistance. We will understand this problem in the limitation, but the flat part where we are interested in is coming from the temperature. Like we can correlate this value of the spectrum to the 4 kbtr and get the temperature. Here I have done opposite. I have done all the measurement at room temperature and showed that for when I vary the value of the resistance, the amount of the power in the spectrum varies as R. So on the right hand side, what I have plotted, the value of the resistance on the x-axis, on the y-axis, the flat part of the where I'm getting this flat part of the spectrum. And then this is the red is the data point, and 4 kTr is the fit to the data, and which is quite in agreement what I am expected to see. So the cross correlation does work. However, if I do not do the cross correlation and I try to use only one channel, what will happen? So I tried my experiment with two type of amplifiers, the chips that was there on the amplifier. So there was one LT1115 and another one was AD743. So there are four preamps, which is are containing, two of them are containing LT1115 and two are containing AD743. If your if I'm using only one channel like autocorrelation, then I'm getting these points in case of AD743, I'm getting the triangular one when they are not correlated. And in case of LT1115, I'm getting this squares with holes. This is in case of LT1115. And it suggests that LT1115 has a more inherent noise than AD743. So best preamplifier we should use for our measurement is AD743. So, and this is the uncorrelated. Now, when we do the cross correlation, what we find, the results improve significantly, and this dotted line shows the theoretical values. This blue data points is taken from AD743. The red data points is taken from LT1115. So the cross correlation from LT1115 is good enough for the low value of the resistance, but as soon as you increase the value of the input resistance, like the device that we measured, it start deviating. But AD743 continues till 100 kilohertz, 100 kilo ohm. This is, I'm showing just 10 kilo ohm, but it does work for 100 kilo ohm that I have shown earlier, I think. Yeah, here I have shown this works till 100 kilo ohm and then it start deviating. So in normal life, in like generally, there is no preamplifier which can be versatile and can be used for infinite range of frequency or infinite range of the resistance. So all the preamplifier you get from the market, some are from the audio circuit, some are from the RF circuit, some are from the displays. So they have their specs, and accordingly you need to choose the electronic amplifier when to apply in your circuit. So for my purpose, I have idea, like I generate or I gained experience that which sort of component I should use to measure the noise across the semiconducting or the metallic samples. So ultimately, there is always limitations, and you can design your experiment knowing your limitations. So first of all, I need to understand why I'm getting those weird kind of one like behavior in the thermal noise. Then let's assume an amplifier, then how it could have been done. So let's model it in a noise equivalent circuit. So basically one actual preamplifier is shown here with an assumption of an ideal noiseless operational amplifier, which is powered by the plus minus VCC supply. When you assume like general, a normal operation, a real life amplifier, you need to associate some noise because it always has some noise, electronic noise. There are two types of noise associated in preamps. These are the basic ones. One is the current noise that comes into the series with the leads of the voltage probes, and the voltage noise which comes in the in one of the end of the, which is this is just I will say convention to define the voltage noise on the plus end and current noise with respect to the ground to the voltage probe. So we define the current noise and the voltage noise associated to the ideal noiseless preamp. Then assume assume that we have two such preamplifiers which is connected to a single resistance. What will happen when you connect it? Your current noises will flow through the device, right? The current noise, they will bias to your sample, and they will cause additional drop of the voltage, right? Because this is having its own fluctuation, and when there is a flow of current, you will see I into R, like IN1N plus I2N into R, which is flowing through the device under test. So this will cause additional noise in the cross correlation spectrum, and this will also have the information of whatever, how the device, how your preamplifiers are being made. Like if these preamplifier having noise, specifically the current noise, the high current noise preamplifier will give you the of bad signal as far as the thermal noise is concerned. So you can model it the for a single amplifier can be modeled as thermal noise of this thermal noise from the sample plus the voltage noise square and plus uh, current noise. And when you have two such preamplifier, this can be modeled as this. And actually, if you see the parameters or the data sheet, the parameters on the data sheet of this product, you will see these values over there. So you say the LT1115 0.9 nanovolts and its current noise is 2.2 picoampere per square root of hertz, and the bandwidth is 40 megahertz. So see, the voltage noise is less for the LT1115 compared to the 8743. But if you see the current noise, which is 2.2 picoampere, and for 8745 is a 6.93 meter ampere per square root of hertz. This is pico means 10 raised to power minus 12 and femto means 10 raised to power minus 15. So basically it is 3 order of magnitude less, approximately 500 to 1000 times less current noise in 8743. That is why the 8743 does perform better for the cross correlation noise measurement in comparison to the LT1115. You can also design your preamplifier and you can also test this even using oscilloscope. But suppose you have one resistor, you amplify your signal using amplifier, then fed your signal to the oscilloscope. Even in the oscilloscope, if you do the time domain analysis, that will also give you the similar results in temperature. So here are the conclusions. So what I have shown here, a noise measurement setup based on two-channel cross correlation, and it validates the thermal noise of known resistors. Conversely, if you know the resistors, you can do the temperature measurement. That is what I'm doing in current postdoc. I'm doing this noise measurement down to 10 millikelvin or so. So the noise signal become very, very, very less. It is 100 times less than a nanovolt. So I'm picking something like 10 picovolts. Okay, 10 to 100 picovolts. So this is really, really hard but the concept is very, very similar. Exactly same concept. You can pick signals of picovolts and then you amplify at very low temperature at 4.2 Kelvin, and then you come some amplification at room temperature, then you fed to the DAC, then you fed to the computer and do the analysis and get the temperature. So this is all from me, and if you have any questions, I'm very happy to answer.
Okay. Sir, thank you so much for an insightful presentation and sharing your valuable knowledge with us. And I was really impressed to see all your slides besides the scientific findings correlating the theories of your scientific finding with the positive quotes like hope is always there, cross correlation of two, and then patience always pays, effect of longer averaging time, and ultimately nothing is perfect with limitations. So and I am sure that there might be some participants who would like to ask questions. So I kindly request the participants, if you have any queries and questions from our resource persons talk, kindly unmute yourself to ask your question. Okay, I think there is no questions. I think it's clear enough. Your presentation is clear enough from your slides. So once again, sir, thank you so much for sparing your valuable time and accepting our humble request, rescheduling your time and adjusting with ours. Once again, thank you so much. And we are really thankful to our principal, Priscilla Rimsiama, for his cooperation, support, and to all our participants who have been joining from the first night. And we kindly request your presence for the upcoming night, which is the last night. And please do join us again tomorrow night at the same time, 8 p.m. Uh, until then, stay safe. Good night. Thank you, everyone.
Thank you for everyone.